So for this question, we're taking a look at these four different molecules and determining whether or not they're polar. So first, let's take a look at what the geometries of each of these molecules will look like. So for our first one, we have OCl2. Our central atom will be oxygen. As you notice, there's an asterisk next to it because oxygen is technically more electronegative compared to the chlorines. So this is an exception to the rule that we have established before. But the number of valence electrons for this molecule is equal to 20. And you might get a shape that looks like this, or a geometry that looks like this, where it is a tetrahedral geometry, but it is bent because there are two lone pairs. So because the chlorines are less electronegative compared to the oxygen, its electron density will be pulled closer to the oxygen and away from the chlorines. So in that case, you will have a partially negative charge for the oxygen and a partially positive charge and a partially positive charge also for the chlorines. So because of this, you will actually get a polar molecule here because there is an overall dipole moment pointing up. So this bar right here indicates a partially positive charge here where the chlorines are located, and this arrow here indicates where the partially negative charge is. So it's going through the molecule like this. So this is a polar molecule. Let's take a look at another option. So take a look at SeF2. So our central atom is selenium, and our valence electrons is equal to 20, so we get a molecule that looks like this. So again, a bent-shaped molecule. And because here selenium is less electronegative compared to the chlorines, you're actually going to have a partially positive charge here and a partially negative charge for each of the chlorines here. Because the chlorines are more electronegative, they're going to draw more electron density closer to itself, and it's going to pull away some of the electrons from the selenium, making it partially positive. So if that's the case, we're also going to get a dipole moment here, which makes it a polar molecule, but our arrows are going to be pointing in the opposite direction because our chlorines are partially negative and our seleniums are partially positive, as indicated here. So next, let's take a look at OF2. So our central atom is oxygen, and we're going to have valence electrons equal to 20. So taking a look at this, I also should have an asterisk here to indicate, actually, never mind, apologies. Actually, oxygen is the least electronegative atom in OF2. So that is correct. So taking a look at this molecule here, we can see the fluorines are more electronegative, so electron density is going to be pulled closer towards it. So each of the fluorines should have a partially negative charge, and the oxygen has a partially positive charge. So our dipole moment, we're going to have pointing down, and it is going to be a polar molecule. I think this drawing is obscuring the bar right here, but that is a positive sign over there. Okay, so let's take a look at our final molecule. We have NCl3. So our central atom is N. We have a total number of valence electrons here equal to 26. And here is the molecule you might have drawn for it. So here, the nitrogen is not as electronegative compared to each of the chlorines. So each of these chlorines are going to have a partially negative charge because it's going to be pulling some electron density away from the nitrogen. So the nitrogen will have a partially positive charge here. So this will make it a polar molecule also because we have an overall dipole moment that is pointing down, because if you imagine each of these chlorines kind of pointing downwards and our nitrogen sticking up, it's like almost like a tent shape, then we have this dipole moment going through the nitrogen where a lot of the partially negative charges are concentrated at the bottom, and the nitrogen is partially positive.